Hi there, my name is Eric, and today's topic for this video is separable differential equations. I have a whole assignment that I've sent out to my students. We're not going to work every problem here. Try to keep this video down to 20 minutes or so. Separable differential equations, when they are separable, end up with some kind of a function of y times, it's got to be times the differential dy, equivalent to some kind of a function of x multiplied by the differential dx. If you can get an equation into this form, then you can proceed with antiderivatives. It's not always easy to get this form. Sometimes it's very easy though. And today I'll try to give you a variety of problems. I'll work them pretty fast. And then if you see me go past a problem that you would like to watch solved, leave a note and maybe I'll make another video. Okay? But that's the goal right there. That's what we're striving for. Now I mentioned that sometimes this is very, very easy. Such as in this first problem. It's really easy to solve that and to separate it first, I should say. The problem says dy over dx equals y over x. Well, anytime two fractions are equal to each other, sometimes it's a very good idea just to take, cross products, cross multiply. If you do that, multiplying this way, you get y times dx. Multiplying this way, you get x times dy. Now that's not separated because this is a y expression with the x differential, and this is an x expression with a y differential. So next, what you might do is divide both sides by y and x, like both factors, just to save time. And when you do that, these y's cancel, and these x's cancel, and you get 1 over y dy is 1 over x dx. That's the form we want. So now it's time for antiderivative time. That's right. Antiderivative on the left, antiderivative on the right. And of course, both of these are natural logs. So you get natural log, absolute value of y, natural log, absolute value of x. And either on the left or the right, and I guess you could put it on both, but it's pointless, put a constant of integration. Okay, I think the goal is to have this solved for y. We want y to be a calculation of x. Okay, dependent, independent. In any case, what you're going to do now to get this y out of this log is use both sides as if they were exponents sitting in a power above the base e. That would look like this. So clearly this side becomes just absolute value of y. And this side can be written as e to the natural log of x, absolute value of x, times e to the b. Now, for the same reason that this became absolute value of y, this can become absolute value of x. And then you can, if you so desire, give this e to the b structure. You see, b is any real number you want, positive, negative, decimal fraction, whatever you want. And so in some sense, this constant is arbitrary also, although it does have to be positive because any power of e is positive. So right here you might say something like, let c equal e to the b. And then put c over here. And last but not least, you are going to take this absolute value off. and set this equal to plus or minus c times the absolute value of x. Pretty easy? Okay. Now you may wonder, why can't we take the absolute value of x off there? And I'm thinking, yeah, I think we could, because that would be accounted for by the fact that you can have either a positive constant or a negative constant. So maybe the best answer looks like this. Okay? So that was problem 1. I'm looking at problem 2 here, and it appears also to have some merit. So we're going to go and look through at that one now. So it says dy dx is equal to x cubed over 1 plus x to the 4th times y. If you multiply both sides of this by dx, like this, you will have dy equals x cubed over 1 plus x to the 4th times y times dx. And then the only thing that's out of place at this point is this y. Because remember, you want an x expression times dx, you want a y expression times dy, and that would be achieved just by going to both sides of this and multiplying it by y. These will cancel, and we will be ready for antiderivatives. Okay. A pretty good way to handle this next step is, yes, put an antiderivative on both sides. And this one is pretty easy, so I'll go ahead and take care of that. I just take the exponent of 1, I elevate it to a square, I divide by that new exponent, and we're good. This other side, though, is not quite so easy. I would recommend doing it as a side problem, and perhaps changing variables. So let's go take a look at this problem on the side. You may wish to rewrite that like this. And then go replace this denominator with your favorite letter. I can almost hear one of my students yelling out, M, I want M. Her first name starts with an M. So let M represent 1 plus x to the 4th. The differential dm is just given by this little formula here. You just have to take the derivative of this, and don't forget multiply by dx. Now, if you compare what I have right here to what's on the right side of this equation, the only difference is there's a factor of 4 here. If it weren't there, I could do a direct substitution and replace that whole box with a dm. What we're going to do is almost that easy. We're just going to divide both sides of this differential by 4. To obtain 1/4 dm is x cubed dx. Now, these are equivalent. Exactly the same. And this equal sign gives us authority to replace this box with 1/4 dm. So in the next line, you have 1 over m, and you replace this box with 1/4 dm. Actually, the 1/4 can go here, or even outside of the antiderivative. Some people are more comfortable if you write it like this. Okay, so what's the antiderivative of 1 over m? And if you didn't notice, the replacement that I did here was based upon this definition right here. Since these are equal, m can take the place of that. The goal was to get rid of all x's, all x differentials, and just go into a whole new variable. And I'm there, and I'm ready to do the antiderivative, and it's natural log of the absolute value of m. You know, plus a constant. Now you might want to put, in fact you should put what n is equal to back in there. And I'm going to go ahead and write that right over here. And put my constant of integration, b, c, a, whatever you like. And carry on from here. Remember what the goal is? To have a closed formula for y. From information about a derivative, I'm basically trying to go from y prime back to y. And we're very, very close to the end here. The next thing to do is to multiply both sides of this equation by 2, so as to cancel the half. So that would look like this. And the whole reason was what again? You had to cancel the half, so now I have y squared. Over here I have 2 times the fourth, that's 1/2. And I also have 2 times b. Now if you're so inclined, since b is an arbitrary constant, 2b is also an arbitrary constant.
Custodian, please come to the main office to sign out your substitute custodian. Thank you.
Wasn't that charming? So, we're going to replace 2b with c. And I'm going to take the square root of both sides. So that will look like this. Anybody have an objection? Yeah, you probably should, because this is clearly a positive thing because it's squared. Being equal to this means this has to be a positive thing too. But when I take the square off of the y, how do we know that that wasn't negative? And so you need to put a plus or minus here, and it's not optional, and it's an important part of the problem. Okay, well, would you like to do one more? Let's solve a third separable differential equation. Now, this one is challenging in the sense that it doesn't have sort of the built-in multiplications and divisions that we need. And so you're going to have to do some factoring to get this thing to work. I'll show you what I mean. In the problem set I'm giving to my students, I have something like this. It's problem 5. It's a real mess. Because you're never going to end up with something like this. Which you can then go do antiderivatives to on both sides. You're not going to be able to separate this thing with all these additions and subtractions up here. Your goal is to have multiplications and divisions. And so you may have learned in an algebra class something called factoring by grouping. And so that's what we're going to do here. Notice how both these terms have x squared. You're going to take x squared out of these two terms. And when you take x squared out of the two terms, either right or left side of the parentheses, it doesn't matter, you are left with a 1 and a minus y. You see that? Okay, this next step's a little harder to see, maybe, unless you've done a lot of factoring by grouping. In this next step, what you're going to do is put the 1 minus y that you see here in parentheses, and you're going to multiply it by 1. For what reason? Because you're now supposed to notice that you've got an expression essentially with two terms in it, and both terms have a factor of 1 minus y. So now you're going to take that out. See, all that factoring you learned, you had no idea how important it would be someday. Take the 1 minus y out, and what's left? Well, the only thing left here is 1. On the other side of the plus sign, the only thing left is x squared. Okay, where I had no multiplication before, sure have it now. And in order to achieve that separated look that I showed you a minute ago, or twice now, multiply both sides of this by dx, so that these cancel, and then divide both sides by 1 plus x squared. Or excuse me, divide both sides by 1 minus y. Right, because we've got all our x's established over here with the x differential. This is the one that's out of place. So you divide by 1 minus y, like that, and you get this. Okay, that's separated, and it's ready for antiderivatives. So we'll go ahead and do this on the left and on the right. Right side's probably a little bit easier. You can just use things like the power rule. For example, x squared goes up to x cubed, you know that. And you divide by that new exponent. The antiderivative of 1, well, okay, let's see. When you do derivatives, quadratic things go to linear things, and linear things go to constant things. So when you do antiderivatives, a constant like this would go back up to linear. As soon as I write this down, it should be pretty clear. The derivative of x is 1. So yes, it's the correct antiderivative. Put a constant over here like that, perhaps. Now, I've been avoiding this. We can do substitution here and use differentials and go into a new variable. Or you can just take my word for it that this is the natural log of the absolute value of 1 minus y times negative 1. And if you're wondering why you'd have to have a negative 1 there, it's because of the chain rule. Okay, so I'm not really focusing on the chain rule right now, but that is the reason if you're curious about it. You know, go do your research there, okay? So I'm going to divide everything by negative 1. And that's going to make everything on this side negative. I'm going to raise everything not to the e power. We're going to use these as exponents above bases of e, like this. And I'm running out of space to show you what comes next, so I may have to go back to the top over here next. But right here, you have absolute value of 1 minus y, clearly, right? And then on this side, I'm going to write this as e to the negative x minus 1/3 x cubed times e to the negative b. In other words, I split this off using a property from algebra where you multiply two powers that have the same base and you can add the exponents together, right, as a single power. That's basically just that property backwards. Okay, we're actually getting pretty close to the end here. What we're going to do is we're going to designate the letter C to represent e to the negative b. So that looks like this. Times C. I'll probably end up moving the C over to here in just a minute. Now I'm going to peel off these absolute values. I like to call that step exfoliate. But when you do that, remember, you have to put a plus or minus over here. And this is a long problem, but whew, we're almost done. Go ahead and subtract 1 from both sides. Like that. And then multiply both sides by -1 so that the y is positive. And that would end up making, well, what's plus or minus c times -1? We don't know if c is plus or minus. We're taking into account both possibilities. Multiplying by -1 is really just going to flip-flop them. It's still going to be plus or minus c. But this will end up being plus 1 because -1 times -1 is 1. That's my solution. Hopefully I didn't make any mistakes anywhere. I think that's enough for this video. My name's Eric. If you're my student, I miss you. If you're just out there on the web trying to learn, I hope I was able to help. Have a good day.